All right, hey everyone. So we are going to talk about NMR today. And there's two main types of NMR. There's proton NMR and carbon NMR. We're focusing only on the proton NMR today. And we're even going to skip through a lot of stuff in this lecture because I posted a video that someone else made that goes over all the basics of NMR, which I think is helpful if you're interested in the theory behind it. But for now, we're going to talk about how to use it because that's where most people get stuck. So let's get started. Okay, the very first thing that you're going to want to do with NMR is learn the different types of quote-unquote proton signals. So when we talk about proton, we're talking about a hydrogen. And the reason that's called a proton, by the way, is this. So when we say proton, we're specifically talking about an H plus ion, but here's why. Do you remember that the number that is in front of things on the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, how they're ordered, that's called their atomic number. The atomic number is the number of protons they have. So hydrogen has 1 proton, helium has 2 protons, lithium, beryllium, etc. So a proton is something that we say it's like hydrogen, but if we were to draw hydrogen out, let's say we make a little sphere, it's got 1 proton in there. Hopefully you agree it also has an electron, right? That's kind of floating around if it's neutral hydrogen. But for a proton, if we have an H plus atom, this would have 1 proton, but it's lost an electron to become a positive charge thing, and therefore all a H plus ion is a proton. It's just a proton chilling, and so that's what we call it, a proton. Okay, it doesn't need any anything. What is the word I'm looking for? A neutron in the middle to hold any glue together, to hold those protons together, because again, it's just 1 single proton. Okay, so back to the important stuff. When you're given a molecule from here on out that you're analyzing via proton NMR, the first thing you want to do is look for the various numbers of different protons. So here, this is symmetrical. Okay, this molecule is symmetrical. And so the protons here are exactly equivalent to the protons here. We could flip this molecule around and they'd look exactly the same. So on an NMR, there's only 1 type of proton, only 1 type of hydrogen atom there. And so they're all equivalent. This one and this one are the same, and you only end up with 1 signal on an NMR. All right, and then we go over here. We have this CH2 is attached to a chlorine, and this CH3 is attached to the CH2 attached to the chlorine. So these are 2 different kinds of protons. They're not identical, though. So this would be one, and this would be another. Now something to start thinking about. This one will be what we call downshifted, and I'll just start throwing random stuff at you, but downshifted because it's closer to the chlorine. So when something's closer to an electronegative atom, it's going to be what we call downshifted. Okay. Then we have this one, okay? Hopefully you agree, this and this, even though it kind of looks like there's symmetry, a CH3 is not the same as a CH2, so there is not symmetry. This CH3 is different than this one, which is different than that one. So there's 3 different groups, and this would produce 3 different signals. All right, so the question says, how many does this atom contain, aka a pentane? So if we draw out a pentane, if you look, there is a plane of symmetry, right through here. So these 2 H pluses, which are on that, would produce 1 signal. Let's grab some colored pencils. Okay, this one, these 2 would be another signal. And last but not least, these 2 would be another signal. My greens have not been working today. Why? Good thing I had 3 green pens with me this morning. Okay, so you'd get 3 different signals from this one particular molecule. I think I'm going to just rip the Band-Aid off and do this lecture the way I want to. So let's start talking about what these signals would look like for a molecule like this. In fact, screw it, I do what I want. Let's do something like this. Okay, let's go back to where we had a CH3 to a CH2 to a Cl. Okay, if I were to draw it out, it'd be a Cl, and then it'd be like douche, douche. Cool. So you got a CH2 here, a CH3 here, and then the Cl. So if I asked you how many different proton groups are on this, I hope you would say 2, because we have one here, and we have another one here, group-wise, right? We know that there's 2 hydrogens here, and we know that there's 3 hydrogens here. Okay. Let's start talking about what would happen in an NMR. So, an NMR is usually a line like this, where the number gets bigger as you go to the left, which is very different than we're used to. So the number is going to go bigger as you go to the left. So we call this downfield, and we call that upfield. So here we have 2 hydrogens, and here we have 3 hydrogens. So the signal that this one will produce, we say will have an integration of 2, because there's 2 hydrogens. And the signal that this one produces will have an integration of 3. This is an integration. In other words, the amount of area it takes up. So this will be 2, and this will be 3. And here's how it works. Because this one, again, is closer to the chlorine, the more electronegative atom, it's going to be further downfield. So the signal that this one will produce will be down here. Okay, so I'll just go ahead and write, it's going to have an integration of 2, and it'll be down here. The next thing you look at is the neighbors. So this carbon right here is attached to this one right here, which has 3 neighbors. There's something called the N+1 rule. And the N+1 rule essentially says you look at the number of hydrogens something has, the neighbor has, and you add 1. And you could think of as the number, or you could even think about it as the number of neighbors plus 1. So this signal right here has 3 neighbors, plus 1 would be 4, and so the signal that this thing would produce would have 4 lines like this, and we'd have an integral of 2. Another way many times people draw it is like this, because that's actually what it ends up looking like, but it comes out a little cleaner when you draw them like this. Okay, and then we have this other one. I'm gonna go like this so you can separate what we're drawing versus that. So this other signal would be further upfield because it's not as close to the chlorine. This one has 3 hydrogens, so its integration will be 3 again. But its neighbor is this one right here, which has 2 hydrogens. 2 plus 1 is 3. So this would have 3 signals. The other way it might be drawn is like that. We'll get into the numbers in a little bit, but this would be essentially the basic NMR spectra of this thing right here. I should say spectrum. All right, let's go ahead and move on. Actually, let's do another example, shall we? We shall. Okay. Let's do something like this. Okay. So first thing, again, is always find the different number of hydrogens. I have 1 here, 2 here, 3 there, and 4 there. And I think I decided what I'm going to do. I'm going to draw them in colored pencil. Okay, or colors. So the one that's attached to the bromine is going to be the furthest downfield. So if we are going to get an NMR out of this hydrogen that's right there, hopefully you agree there's 1, would be the one that's way down here. Now this has 3, this one has 2, and this one has 3. Okay. Well, let's start with the one that's the farthest downfield. Okay, this blue one. I hope you agree that this blue thing would have an integral of 1 because it has 1 hydrogen. So its integral is 1. But now let's look to the signals. Do you remember that we follow the N+1 rule? So you count how many neighbors this particular carbon has, and then you add 1. So this carbon has 1, 2, but then also over here, 3, 4, 5. So 5 plus 1 is 6, so its signal will be 6. Okay. You'll eventually see that all the odd numbers have a high peak, and all the even numbers are even right there. Okay. So it would be what we call a sextuplet. It has 6 different peaks. And now we've taken care of that one. Then we move on to the next one, whichever one you choose. Of these two, this one's more affected by the bromine because it doesn't have the carbon over here, but these two would be kind of hard to decipher which one's going where from our knowledge right now. So it doesn't really matter which order we're going to put it in, but hopefully you agree this one has 3 hydrogens, so this one would be an integral of 3. The next thing you pay attention to is how many neighbors it has. Well, it's attached to this carbon, which has just 1. You only look to the ones that are directly attached. So this has just 1 neighbor. Okay, so n plus 1 would be 2, or 1 plus 1, which would equal 2. And so this would be a doublet, like this. Okay, so we've taken care of this one. We've taken care of that one. Now we move on to the green one. This is close to bromine, so it's still going to be more downfield than this one. This has 2 hydrogens on it. 2 hydrogens means its integral is going to be a 2. And I hope you agree. If we count neighbors, we have 1, 2, 3, and then this one over here makes 4. 4 plus 1 is 5, okay, and we get a quintuplet. Let's see, 1, 2, 3, 4, 5. Like I said, anytime you have an odd number, that peak is going to be higher. When you have even numbers, your middle peaks are going to be even, or about the same size. Okay, and last but not least, we have this methyl group over here. The methyl group has 3 hydrogens on it, so its integral is 3. Its neighbors, it has 1, or its neighbors, excuse me, I started counting that. Its neighbors are only this one right here, which is 2. 2 plus 1 equals 3. So this will be a triplet signal. And now we've just essentially drawn relative NMR of this compound right here, which we should name. It's 2-bromo-butane. Okay. So going back over here, the reason I stopped was because I knew you guys could do this NMR if we just took a few seconds to learn about it. So rather than just learning all these little things and then building up, I think we can just go straight for the throat. Let's do it. So let's say we're figuring this one out. Okay, so the number of hydrogens this one has is 2. This one, that one, that one, that one, and 1, 2, 3, 1, 2, 3. Okay, so these protons here and here are going to be a different signal than these two there, which will be a different signal than that one. But these will have the exact same signal as these, as those. So there's only 3 signals we expect. So let's go through each one. The one in the middle will be slightly more downshifted. They all will be very close because there's no electronegative atom in there pulling anything one way or the other. So this will be the more downshifted, followed by this, followed by that. Okay, so let's just start with this central one real quick. Okay, so the integration of it, there are 2 hydrogens. So the integration will be 2. Okay. The next thing, we want to count neighbors. And this is where it gets a little funky. You only want to count 1 set of neighbors. Okay, so even though it has these 1, 2, and 1, 2 neighbors, we're only going to count one of them. So we'll give it, in other words, these 2 neighbors right there. shouldn't say one of them, but one of the neighbor's carbons. So we got 2 here and 2 here, so our N is just 2. 2 plus 1 equals 3, so this will be a triplet, like that. Now we move on to the blue over here. There are 4 hydrogens on the blue, so our integral is 4. But when you do the neighbors, you only look to the neighbors of one of these sides. Okay. So here you have these 2 neighbors there, and those 3 neighbors there for a total of 5. 5 plus 1 equals 6, so you'll have a 6, a sextuplet as it would be called. Last but not least, we come to these ends. There are a total of 6 hydrogens included, so our integral will be 6. But then we look to just one neighbor. Here I have one neighbor. It's got 2 hydrogens on it. 2 plus 1 equals 3, and you'll have a triplet as a response. So that is relatively what it would look like. Now you will find that some places, if you have an integral of 2, an integral of 4, an integral of 6, they'll divide them by a common denominator, which would be 2 in each of those, so you'll get a 1, 2, and a 3. That's possible. So what I'm saying is they'll divide that one by 2, that by 2, and that by 2, so you get an integral of 1, integral of 2, integral of 3. Expect on your exam for me to always give you the appropriate number, and sometimes we'll write it as 2H, 4H, 6H, instead of using the integral signal, which tells you there are exactly 2 hydrogens in this group, there are 4 hydrogens in that group, and there are 6 hydrogens in that group. Okay, I'm skipping through, well, maybe. This is a good example real quick. We won't do this one, but it's a nice example. So here, if I asked you how many different proton groups are in this, I want you to recognize that these 2 are exactly the same. This is attached to the triangle, and this is attached to the triangle being cyclopropane. So this and this are exactly the same, so this only counts as one group. Then this carbon right here has 1, 2, 3, 4 things on it. There are no hydrogens on it. This one right here has boom, boom. It's got 2 hydrogens. So this is another group. I got a call, sorry. Okay, and this one is another one, and it's got 1 hydrogen right there. Okay, I didn't draw these 3, so let's just be consistent. Okay, and then we have this hydrogen right there. So overall, we got 1, 2, 3, 4 different kind of NMR signals. All right, we're not going to do homotopic or anisottopic. Let's skip over that. Doesn't matter. I just care that you can read an NMR and make an NMR. Okay, so how many NMR signals would you expect for each of these compounds? Just asking how many different groups of hydrogens there are. We have 1 here, 1 here, 1 here, and 1 there. So you'd expect 4 different ones. If I asked you where the signals would be, hopefully you agree this one would be the most downfield, and then this one would be the farthest upfield. Okay, then for these, 1, 2, 3, and then 4. All right, oxygen's more electronegative, so this one right here would be the more downfield. The kind of the one we've been starting with. We like to start with the more downfield one, followed by this one, followed by that one, and then that one. Okay. Actually, now that I see it, this one, sorry, and this one are both attached to an oxygen. They'd both be downfield, followed by that one and that one, excuse me. So like downfield wise, 1, 2, 3, and 4. We're 1 and 2, could be relatively close to each other. Okay, then it tells you, even though we've talked about it a lot, protons near electronegative atoms are what we call de-shielded, because the electronegative things draw the electrons away from these protons, which makes their signal pop. Okay. So using that information, which of the following would absorb farther downfield? So if you have propane like that, or dimethyl ether like this. So hopefully you agree these are attached to electronegative atom, more electronegative. So these, both of these signals, here and here, which happen to be identical, would be more downfield, excuse me, because they're more shielded. Okay, then we have this one, or this one, very similar. So we have this versus this. But we know on a periodic table, or cannot clean out fridge, that oxygen's more electronegative than sulfur because it's more up and to the right. Remember, electronegativity goes that way. So if it's more up and to the right, this one has a more electronegative atom, and this one would absorb farther downfield. Here are the specific shifts. You will be given this on your exam. So if you want to know specific numbers, for example, if you have a hydrogen that's attached after a double bond over here, it would be this, and it gives you some specific numbers, which are helpful. The main ones that we run into are, let's see, do I even see it? Are these right here. So when we have some kind of nitrogen, oxygen, or some, like an alkyl halide attached to a proton, that's going to be farther shifted downfield, like 2.5 to 4-ish. Okay, so then we have this. It wants us to figure out the number of protons and then kind of rank them for the direction that they're going. So let's say we have this one, and this. Okay. Let's go ahead and call the purple one A, the green one B, and the blue one C. If I asked you which one's going to be which set of protons is going to be shifted farthest downfield, I hope you agree it's going to be A, and you'd be right. But this looks like so much fun. I think we should do this NMR. So let's do it. Let's see what it would look like. Okay. So we have a Cl, and then that, and a Br. Okay. I hope you agree that the most electronegative atom between bromine and chlorine is chlorine. Chlorine's farther up and to the right on the periodic table than bromine. So these protons, the purple ones I just drew, are going to be the farthest downfield. We also know that when protons attach directly to a bromine, that it's somewhere in between the 2.5 to 4 range, according to the chart we just looked at. So these purple ones will have an integral of 2 because there's 2 of them. And then you just ask about the neighbors. Well, these neighbors, there's 1, 2 protons. And of the blue, there's 1, 2 protons. Okay, so this, again, back to the purple, there's 2 protons. And then looking at its neighbors, there's 1, 2. Remember the 2 plus 1 rule. 2 plus 1 equals 3. So these will have a triplet signal, farthest downfield. Then the next farthest downfield will be this one because it's directly attached to this. So we know that this has 2 protons, so its integral again will be 2. And it's attached directly to something here, which has 2 protons. And so once again, we'll do 2 plus 1 equals 3, and you'll have a triplet signal there. And last but not least is this green one in the middle. Its integral is also 2 protons. Again, on all these, we could write 2H, 2H, and 2H. So it's also 2 protons, and then when we look to the neighbors, to the left, it's got 1, 2, and to the right, it has 1, 2. So 4 plus 1, for a total of 4 neighbors plus 1 gives us 5, and it would have a quintuplet response. All right, see, wasn't it fun? Okay. Then we move to this one. There's one signal right there. This one's definitely different. This one has nothing, right? There's no hydrogen on this carbon, but there's 3 there, and they are all identical. Methyl group, methyl group, methyl group, all attached to the same thing. So this would only have 3 different signals. How each one would go, if this is our B, this is our C, and this one is our A. Our B, the one that's closest to both of them, will be farther downfield. I shouldn't have done that. Sorry, I didn't mean to use purple. Whoops. Our B is going to be farther downfield than our A. Again, because the B's got 2 electronegative things pulling, deshielding it, and the A only has 1 electronegative thing deshielding it. And then poor lonely C over here has essentially none. Okay, so let's go ahead and let's try to do this one. It looks like fun, right? And it'll provide a lot of good insight. So okay, it says the area under the signal is proportional to the number of, yeah, we already know that. I don't know why I'm moving on. So here, oh, boom, boom, oh. And then here, boom, boom, boom. So this one has 3 hydrogens. This middle one, which we said is going to be the farthest shifted downfield, has 2 hydrogens. This has nothing. And this has 3 hydrogens on all of these methyl groups. This will be an integral of 9 because there are a total of 9 identical hydrogen groups. Okay. So let's go ahead and get started. We know we go like that. We know this is the one we're starting with. It's closest to the electronegative atoms, and it will have an integral of 2. Then you look to the left and to the right. This oxygen has no neighbors, and this oxygen has no neighbors. And therefore, 0 plus 1 equals 1, and this will be what we call a singlet, just one single signal. Okay, now we move on to the purple, because it's the next further downfield, because it's the next closest to an oxygen. It has 3 hydrogens, so it'll be an integral of 3. And if you look at it, it also is attached to an oxygen, and it has no neighbors. So it will also be a singlet. So 0 plus 1 equals 1. And last but not least, we have this one. I said it would be an integral of 9 because we have a total of 9 neighbors. And usually these things are kind of relative in height. Like that will be, I'm getting a call, sorry. Usually these will be relative in height. Like this will be taller than this one. And this 9 would obviously be quite big. So if you look here, this is the carbon. You look to this thing and ask if it has any neighbors. It does not. This is a singlet as well. That was a fun one. Interesting. All right, and that would be the spectrum of that. Okay, it says the area under the NMR is proportional to the number of absorbing protons. So kind of like I was just saying, the 9 should be technically 3 times bigger. This one should be like smaller, this one should be bigger, and this should be like 9. So it should be like a 2 to 3 to 9 ratio. And it shows here with this particular example. Let's draw it out to make sure we agree. This is to an O, to a C, and then we have a CH3, CH3, and a CH3. Okay. These 3 are identical protons, and this one is on its own. That's why we got 2 peaks. This TMS is just the standard that's added to essentially say, hey, it's at 0. These, I don't expect them to show up in your exam that I have a TMS standard, but if I do, you just ignore it. So this should give us just two signals. This, we would say, would have an integral of 3. This would have an integral of 9, right? Because there's a total of 9 identical protons. And so it's a 3 to 9, which they just divided it by each one by 3. And that's how I got a relative area of 1 and a relative area of 3. Okay. On this particular example, you have two different kinds of hydrogens. You have this one and this one. This one has more electronegative things on it, so it's going to be more downshielded. It's going to more downfield. It's going to be more shielded. So this one is the one we would have normally started with. We'd say, hey, it's got an integral of 1, and it has the carbon next to it has 2 hydrogens. 2 plus 1 is 3, and that's how you got this 3-peak thing. And same with over here. We started with this one. It would have an integral of 2. And then you look at its neighbor, there's only 1 hydrogen on there. 1 plus 1 is 2. And I should have done that. 2 plus 1 is 3. So 1 plus 1 is 2, and that's why you got the doublet for this one. Okay. So at this point, even though I was planning on just going over the peaks right now, hopefully you're already getting to understand what's going on, and then you're already feeling pretty confident in how you do that anymore. Just some terminology. If you have 1 peak, I've been drawing it like this, or you could also draw it like this. 2 peaks, 3 peaks. Again, with these odd numbers, the middle one's always higher, and they're always getting bigger. 4 peaks. 5 peaks. Be a quintet, and I'm not going through these numbers. Sorry, singlet, doublet, triplet, quartet, quintet, or quintet. A sextet has 6. Maybe 1, 2, 3, 4, 5, 6. A septet has 7. Really high one. That was fun to draw. But hopefully you can kind of see the pattern and how they work. So we'll be using these numbers a lot. If you get a multiplet, there's obviously a lot of neighbors. Okay, I think we've kind of already gone through all this stuff. This starts talking about the n+1 rule. And then last but not least is this one. I mean, we already have the answer for this, but let's do this one anyway, just because we can. So let's say we're trying to draw the NMR spectrum, and we can go like this. Got a CH3 and a CH3. Why drew the C? I hope you agree that these two are identical. Okay. And this one's different. If I asked you which one's going to be the signal most downfield, I hope you agree it's going to be this hydrogen that's on the bromine because it's the closest to the bromine. So that's the one that's going to be the most downfield. So it's going to be the one that has an integral of 1. So it's going to be a tiny peak. It's just little. It's just an integral of 1. And then if you look at the neighbors, it has a total of 1, 2, 3, 4, 5, 6 neighbors. Okay. So if it has a total of 6 neighbors, 6 plus 1 is 7. So it's going to be a septet. So its peak will look like, I'm starting to draw it the way I wasn't going to. Did I do that? Nope, I didn't. Do. That's 7. Okay. So this would be for the green one. All right, and then we go and look at these other signals. Hopefully you agree there's an integral of 6. So it's going to be big. It's going to be 6 times bigger than that. And it has, remember, you're only looking at one of these in its neighbors because they're identical. They'll have the same neighbors. So it has one neighbor, 1, plus 1 is 2. So it's going to be a doublet. Whoa, whoa. And that's why it looks like this. Okay, so hopefully that makes some sense and gives you an idea of how to get started. Now I would move on to the worksheet where I actually go through several examples of NMR and start working on them. All right, bye.